Hello and welcome. I'm Unmukt Gupta. I'm a graduate student in Fernando Escobedo's lab at Cornell University. In this talk, I'm going to share the development of an implicit solvent model for the interfacial configuration of colloidal nanoparticles. So, in recent years, it has become possible to synthesize colloidal nanoparticles with greater precision and repeatability, both in terms of size and their shape conformity. Typically, the formation of highly ordered superstructures from these nanoparticle building blocks is facilitated by restricting the self-assembly process to 2 dimensions. And a common way to do this is to bind the nanoparticles irreversibly to fluid-fluid interfaces. It has been shown that based on their different orientation preferences at the interface, a variety of self-assembled structures are obtained. And these materials are particularly interesting because they exhibit a wide range of functional properties based on their assembled structure. For example, superstructures with square symmetry possess wider band gaps, which potentially implies better electron transport, leading to possibility of better optoelectronic properties. Superstructures with hexagonal symmetries display graphene-like behavior. The ability to assemble nanoparticle building blocks into different superstructures opens up the possibility of materials with tunable properties. There is a growing interest to understand the fundamental kinetic and thermodynamic factors that govern the self-assembly process. The adopted approach is to divide the problem into 2 distinct paradigms. We begin by analyzing the behavior of an isolated nanoparticle at a fluid-fluid interface, and to this end, we can employ 2 complementary methodologies. We can use theoretical modeling, or we can use molecular dynamic simulations, where we explicitly model the solvent molecules and therefore the interface. Now consider the case of an isolated nanoparticle at a planar interface. Its behavior is determined by 2 major characteristics. Firstly, the vertical position of its center of mass h from the interface dividing plane. Secondly, its orientation, which can be described in terms of a quaternion q, or using a convenient Euler angle representation. And since the rotation phi about the vertical axis creates no change with respect to the cylindrically symmetric interface, this rotation phi can be safely ignored. Through free energy calculations, we can show that nanoparticles of size close to 5 nanometer tend to stay adsorbed to the interface with an associated free energy well of about 50 to 100 kBt. The orientation free energy can also be plotted as a function of the Euler angles, where the color bar indicates the free energy in kBt scale, increasing from the most stable state in blue to an intermediate value in white to the least stable states in red. For a cube shape, this dictates the tendency to preferentially stay in the 1-1-1 orientation. Both these characteristics arise from the nanoparticle's tendency to reduce unfavorable contact between the 2 immiscible fluids, and to this end, nanoparticle orients itself in such a way so as to maximize the volume that it excludes from the interfacial region. And based on this fundamental principle, we can come up with physical handles that can be used to directly influence the vertical position and orientation behavior in experiments. As an example, increasing the contact angle between the 2 immiscible fluids leads to an increase in energy of contact between them. This in turn leads to deepening of the free energy wells, leading to stronger vertical position and orientation biases. Similarly, there exists a wide range of distinct orientation behavior corresponding to different nanoparticle shapes, ranging from 100 for a truncated octahedron shape to 1NO for a rhombic cuboctahedron shape to 111 for a cuboctahedron shape. So in this way, solvent explicit MD simulations demonstrate their ability to capture the behavior of an isolated nanoparticle. However, to scale these simulations up to the multi-nanoparticle regime isn't practical, and this is due to the large associated expense of simulating the surrounding fluid molecules. To bridge this gap, we use insights gained from the explicit solvent simulations to develop an implicit solvent model. This model captures the multibody effect of the solvent molecules and therefore of the interface itself, and it does so by overlaying an effective potential of mean force onto each nanoparticle. Moreover, the developed heuristic model needs to be general enough to reproduce the wide range of possible behavior, some of which I'd already shown in a previous slide, and do so in a systematic manner. And secondly, it needs to be accurate. It needs to be doing so with minimum loss of detail. Now I'll give a quick overview of the model. To a first approximation, the effect of an interface on a nanoparticle can be broken down linearly into contributions from the vertical position and the orientation characteristics. The vertical bias can be reproduced by tethering a spring to the nanoparticle's vertical position, h. The resulting parabolic fit is seen as the dotted red line. The scaling parameter kV is a measure of the depth of the free energy well. Along the same lines, for the orientation bias, we need a basis function to define the potential. In other words, an orientation analog of h. Consider an arbitrary orientation Q. Let's also define the HKL feature orientation as the one where the HKL facet is parallel to the interfacial plane, which in this case happens to be the green 111 facet. Now we can define an HKL feature potential given by this expression as the tendency to rotate the nanoparticle from its current orientation towards the feature orientation along the shortest path, and do so as to point the HKL facet at an angle alpha naught from the vertical. Building on that, the overall orientation bias can be defined as a linear superposition of these single feature potentials, wherein each feature could correspond to a hypothetical HKL facet. The variable alpha m is defined as the angle of closest approach, and it forms the basis function for each of these feature potentials. This alpha m parameter is calculated using the quaternion-based orientation constraint, or the COCO method. To replicate the physical system, the COCO method is predicated on three inductive biases. Firstly, the torque is applied continuously in accordance with Euler's rotation theorem, while ensuring rotational invariance about the vertical axis. It also accounts for rotational isometries in symmetric shapes. The closest approach is given by the minimum angle required to reach an equivalent feature orientation. To the free energy of a cube, we fit a single 100 feature potential. We use the COCO method to map the Euler angles to the basis function alpha m 100. The problem then reduces down to an optimization of the alpha naught and kt parameters. The resulting fit captures the orientation behavior both qualitatively and quantitatively. To measure the goodness of fit, we report the coefficient of determination, r square. A value of r square equal to 0.94 can be interpreted as the model's ability to capture approximately 94% of the variance in the data. To improve the degree of this quantitative match, multiple features may be composed, as in the case of this truncated octahedron, where we can use a 111 and a 110 feature potential. To further increase the complexity encoded by the orientation PMF, the angle of closest approach basis functions may be used with any form of potential. Here we show fits using two-parameter Gaussian forms. The high level of quantitative conformity achieved could be crucial for certain applications. In summary, the orientation bias is centered around selection of the relevant feature space and calculation of the corresponding angle of closest approach basis functions. Alpha m embodies a single valued measure of the nanoparticle orientation while still being invariant to its rotational isometries. The feature space Fs can be augmented to account for the PMFs of more complex shapes. And although all possible HKL features may be relevant, some contribute relatively more to the free energy landscape. In this way, the formulation of the orientation bias is analogous to a Fourier series expansion with leading terms dominating local behavior. I will now briefly talk about how the implicit solvent method can be used to study the self-assembly process. To facilitate the formation of highly ordered superstructures, the self-assembly process is separated into two parts. First, nanoparticles are pre-assembled into an unconnected structure which is stabilized by surface-bound ligands. Secondly, the addition of a trigger, typically a chemical one, to displace the ligands leads to the formation of an epitaxially connected superstructure. It is known that the ligand binding energy and surface coverage is facet specific. In other words, the 100 facets become deprotected the fastest, prompting the formation of inter-nanoparticle epitaxial connections between them. To mimic the gradual deprotection of the 100 facets for our simulations, we gradually ramp up the interactions between the 100 facet beads, that is, the red beads, from 0 to some maximum value. To illustrate this, we simulate the assembly of a large array of cuboctahedra using a single 111 feature orientation potential. What you see is a top-down view of the self-assembly of 1024 cuboctahedra. The nanoparticles are colored based on their vertical position with respect to the interfacial plane. The nanoparticles are colored red if they are out of the plane, white if they're on the plane, and blue if they're into the plane. We can see that the nanoparticles assemble into a honeycomb superstructure. We also simulate a range of conditions by slightly changing the strength of the imposed biases and then tabulate our results as a phase map. We observe three major phases: the square monolayer, the honeycomb bilayer, and a disordered phase. It is important to remember that the strength of the biases given by Kv and Kt represent physically relevant measures of the interfacial conditions, nanoparticle size, etc. And these can be correlated to real experimental handles. Most notably, the honeycomb and the square lattices are observed for a wide range of conditions and are of great interest experimentally. The observed phase behavior is an interplay between the three competing forces of vertical position, orientation preference, and internanoparticle bonding. This phase map can be used to create guidelines for the formation of various known superstructures. More importantly, this process can be used to study the phase behavior corresponding to the characteristics displayed by different nanoparticle shapes, solvent combinations, etc.